How'd you do? I'm gonna write a few notes here. This is a good problem to show that acid-free doesn't give you the same as acid, even though they're both Markovnikov. So notice the OH went on the more substituted of the two carbons. The OH went on the more substituted of the two carbons, OH, and it could have equally gone from the front or the back, so no selectivity there. So we have a wedge or a dash possible, right? So we might draw those out, or you might see a straight line with it indicated as plus or minus or racemic. You want to recognize all of those and be able to draw it either way that's asked, okay? So when in doubt, draw it all out. So anyway, this is a perfect illustration of Markovnikov selectivity. I'll just abbreviate Markov. Oh no, I just actually wrote the whole thing, Markovnikov. And then it's also a good illustration of how there's no rearrangement. Compare that to the other one that was Markovnikov, but it's still rearranged. So of the two, these were the two carbons, A and B, that were in the alkene. Neither A nor B got the alcohol because it rearranged. Do the mechanism if you're not sure, convinced, right? It can rearrange to a more stable carbocation. So, but with C plus rearrangement possible. Doesn't mean it always happens. So we got a different product. Not a stereocenter, by the way, either. Hence only one. And then finally, this one down here, anti-Markovnikov. Right over here, anti-Markovnikov. I'll just write Markov. Notice that of the two carbons, B is the one that got the OH. Syn to it would be the H, but since there's two H's here, we don't need to draw the dash and wedge. It doesn't matter. Like if I drew it, it would just, there's another H there. It's not a stereocenter. So sometimes you got to draw it, sometimes you don't. You got to rely on your knowledge of stereochemistry to kind of work your way, navigate that. And that comes with extra practice. So no two problems look alike. Keep doing them, and then you start to see the patterns of logic unfold rather than trying to get a problem style. Okay, let's do our next alkene reaction. I think you're ready to move on from hydrations. We're going to make something different. Notice the deuterium's there. That's just so that we can track what's happening. That's an alkene. In the presence of palladium, platinum, or nickel as a catalyst, we're going to do what's called hydrogenation. Not hydration, hydrogenation, meaning we're adding hydrogen. So H2, and it's a gas. Now this adds syn. It's syn selective. But the nice thing about it is that you don't have to agonize over which carbon gets what, because regiochemistry is irrelevant since they each get an H. So in other words, we could have two H's add syn as wedges. So that means the D's become dashes. And I actually would like it better if I drew it this way. And you should always consider both scenarios, which means if I could have the H's add as both dashes, that means the D's could have been wedges and the H's are dashes underneath. But be careful, because every time we draw both possible enantiomers, make sure they really are enantiomers, because these are actually the same. It's a good exercise to draw both, but always kind of judge and make sure you really did draw something new, right? So if I flip that over, I get the same thing. Okay, so things to note here. Stereoselectivity. Activity. Syn, addition of H across the pi bond. Do I need to talk about regioselectivity? No, because both carbons, they each get an H. You don't have to ask which carbon gets the H. They both get an H. Okay. So the mechanism of this one is interesting because it's almost kind of cartoonish. So what the idea is, we're going to draw this big surface for our catalyst. Let's call it palladium. Platinum or nickel is also common. And in the presence of hydrogen gas, it will actually help break that HH bond and deposit the individual H's onto the surface. So it's coated and ready to react. In comes our alkene. So I'm just going to write it a little more generically with R groups. So if I say it looks like this, R, and then we have another H here. You can see why we like to use D's, because we can confuse the original H's with the new H's, which is why sometimes I end up doing the color coding, which I'll end up doing here. Okay, so the alkene is actually attracted, it's electron rich to the metal surface because the metal itself is electron poor. That's what we know about transition metals. So, and it's actually, these bonds are not fixed. They can actually kind of scoot around and make some room for the alkene to complex. And I'm going to draw the alkene the way we did before, where now I'm going to let those top groups be dashes. So it's coming out at us. So at first I drew it in the plane, and now it's going to kind of come out at us as it deposits and hangs out and maximizes its interaction with that metal surface. So I'm going to indicate that positive interaction right here. So this is confined to one plane. So notice how that's either one, but it could have flipped over and interacted from that side, but it's confined to one plane. This step right here tells us why it's syn. You're going to get those H's come in at the same time. So I'll circle the two nearby H's that can kind of, when that pi bond weakens, and the two H's that can fill that valency as it's associated with the metal, those two nearby ones I'll just circle in red. And there's not a lot of arrow pushing with this, which is what makes it a little, that's why I say it's a little cartoonish, but it at least explains the syn nature. So here's my R groups, R, R, there's my H, and my new H's came from the same side, syn, because that's the alkene. They could have only added at the same time while the alkene was associated. So that's the general idea of the mechanism that helps us understand why we get the syn addition. So now we know what do we do? We just made an alkene into an alkane, right? So we can actually convert alkenes into dihalides, halohydrins, alcohols, ethers, alkanes. We've learned a lot of reactions. So this is the point where we've done so much functional group interconversion, we're ready to put it together. This is the chemists are put to the task to make things, not just one step, but multi-steps. So we're going to start putting some of these together in a multi-step synthesis. So this takes some practice, but here's an example of what we could do. So it kind of skipped down to here. So see how there's two steps? These are two separate steps. This is going to be, every time I have a step 1 and a 2 and a 3 and a 4, those are things we should theoretically be able to isolate at the end. If you say, what if my one step had two steps, like the oxymercuration, demercuration, then you call those A and B in a multi-step synthesis. So over the arrow, we have two separate steps that are two different reactions. So, you know, if you don't recognize this, you might recognize if we had it in our solvent, CCl4, right? So this is to make the dihalide. So I'm going to draw on my H's so I can remember what that's going to look like. And then I'm going to draw my dihalide. Remember those as anti-vicinal dihalide, right? That's the first step. We're going to get an anti-vicinal dihalide. So I'd like to do this scenario where I say this equals dashed on the top, ME, and wedges on the bottom so that I can just turn that toward me, look at it on the side. And let's see, this is a 1, 2, 3 carbon chain. I'm just going to call that PR, propyl. That'll simplify a little bit, right? Okay, so now to draw my anti-framework, I'm going to do that, and I'm going to do the opposite. Those are my chlorines. They're anti in the plane. This is a down carbon because the chlorine's above it. This is an up carbon because the chlorine's below it. Down carbons have dashes and wedges point down. These are my dashes and wedges that need to point down. They can be repeated as drawn. Up carbon gets these dashes and wedges. Let's do it again. Now it's the opposite. We have a down carbon on the back end and an up carbon on the front end. You do that and you will take care of your enantiomers. I drew that out for thoroughness, for practice, but it turns out that it's because this is a two-step synthesis. So this was step 1. Step 2, we're at NaNH2. And we're going to say, how about we have some excess? That means as many equivalents as we need to react. What is NaNH2? It's a strong base. Oh no, so we are going back to another chapter. We are going to take advantage of the fact that when we made a dihalide, we made something with 2 leaving groups. If those 2 leaving groups are subjected to something with a base, we could actually do an elimination, not just 1, but 2, a double elimination, only if we have an anti-beta H. So we can conceivably rotate this to be anti to that, and we can conceivably rotate this to be anti to that. So that means we can get rid of that H and that H to get double E2, which we have previewed that before. So go back to your notes if you're not sure, but so that's why I'm not going to show that in every step great detail because we've done it before. But double E2, right? I'm just going to write that out though. 2 leaving groups, 2 beta H's, excess base. That's the recipe for double E2. What is useful about a double E2? It allows us to access a particular functional group. So here's my methyl that was there. This is carbon A and B. It is now part of an alkyne. And what else was there? The propyl. That's my final answer. Remember to draw those linear, those alkynes. So that's just 2 steps. We're going to work our way up to syntheses that are much longer, but you want to be able to combine chapters worth of reactions. We know how to make alkenes. We know how to react alkenes. Therefore, we are ready to do something that makes alkenes and reacts them. We are ready to do something that reacts alkenes then makes something else, right? So, and the more we add, the more we'll be able to do. So we want to be able to put it in that context, have those individual reactions ready to connect, like a toolbox. They're going to be like our little Lego pieces or tools or parts ready to assemble into anything we're trying to envision. Here's another 2-step synthesis we could do. Step 1, we see this. That's normally on its own. From this chapter, this would make a halohydrin. Let's make it. It's good practice to draw it all out, but notice that this is not even a stereocenter, so that's gonna influence it a little bit. But so here's our H. So if this equals dash wedge methyl dash methyl wedge H, remember halohydrin, still anti, so draw your anti framework. Now remember where the OH goes. Where does it go? The more substituted carbon, right? Follows Markovnikov. So it's the nucleophile. It goes to the more substituted carbon. So this carbon gets the OH, the first one. If this is A and B, A and B, A and B, we're going to have the OH anti to the Cl, the OH anti to the Cl the opposite way. fill in our dashes and wedges that were originally defined here. And you can put the H in if you want to. I will. And now, step 2, another base. What's the base going to do? Na plus, H minus. That's strong enough to deprotonate an alcohol. So we're going to have O minus. Let's go ahead and say excess for good measure. Now we don't actually need excess because it's a 1-to-1. Never mind. Because we're only doing it once. So whether it's that one or 1-to-1, whether it's the other enantiomer, I will write out the mechanism for what we get, but we're not done yet because Cl, I'll just write out that. And then because this isn't a stereocenter, I'm not going to bother writing dashes and wedges for those methyls, just because you want to be able to see when that's appropriate and when it's not. So that's that one. And then this is this one over here. It was up O minus, down chlorine. Well, guess what? We have a O minus adjacent to a Cl. This is a leaving group. This is a nucleophile. We're combining acid base, SN2, and the fact that we can make this from an alkene all in one sort of concept. Attack, kick off. Attack, kick off. It's an internal SN2. So it's not done. So this is an internal SN2. So what is the name of this functional group? This 3-membered ring. Right? So we could have had, as that gets attacked, right? Then we still have our 2 possibilities, whether that's a dash or a wedge. Epoxide. So you can make epoxides now. You can make alkynes, you can make alkoxides, you can make alcohols. I'm writing down the functional group because something about writing that will help kind of log it, right? We need to know what we have at our disposal for future multi-step syntheses. So that's a way to make an epoxide in 2 steps from an alkene. So 1, halohydrin, 2, base. And that's a perfectly acceptable way to make one, but most of the time you're trying to save money and have high yield. And one way to save money is fewer steps. So I'm going to show you a reaction that will make an epoxide in 1 step. Okay. If that was to fail for some reason, we know we could use the 2-step one, right? So it's good to know more than one route, and that's certainly going to happen. But this is an epoxidation of an alkene to go straight to the epoxide, not a 2-step thing that we did before, not a multi-step synthesis. So go from an alkene to an epoxide. What's over the arrow? RCO3H. Let's get comfortable with that. We know what RCO2H is. That's a carboxylic acid. Carboxylic acid. RCO3H is 1 more O. Just like hydrogen peroxide, only with a carbonyl. It's a peroxy acid. Notice the per. The per is always used to kind of indicate an extra O, like water. And then hydrogen peroxide is like water with an extra O, the per acid. So this is a peroxy acid. So it's an acid with an extra O. We need to know that structure to do the mechanism. That's why it's written out here. R can be lots of other things. It can be So don't let that throw you off. The functional part is here. Carbonyl, OOH. This part can be variable. It could be a methyl, it could be a benzene ring, it could be a propyl group. So be understanding that this could change. In fact, I'm going to write an R here to emphasize that. But you might see MeCO3H. You might see it defined, right? So let's put that here, e.g. MeCO3H. There's another one that's really popular called MCPBA, and we'll show you that one next. Metachloroperoxybenzoic acid. But it's the peroxy acid that has the functional group part. The rest is just there because it's usually good for solubility and reaction conditions. Okay, what is this going to do? We have added oxygen. We could say a peroxy acid is an oxidizer. Look at all those oxygens. That's something an oxidizing agent has in common. Other ones you've known from the past, KMNO4, lots of oxygen ratio, high oxygen ratio compared to other compounds. So lots of oxygen for one smaller organic compound. That's a hint that it's an oxidizing agent. That's how it behaves. So let's look at this trans alkene. And I'm going to rely on this approach, this perspective a lot, because stereochemistry matters. It's to remind us that it's flat, and that we can have something approach it from the top or from the bottom. Okay, so we can have, here's our peroxy acid, ROO. We're writing out the whole structure every time. Let's show the peroxy acid approach the alkene from the top. Okay, so it encounters the alkene from the top. We're going to draw, but I need a little rotation first. I'm going to draw the alkene as it is here, but it's the peroxy acid. I'm going to rotate a little bit. This was an H, wasn't it? H, H, H. Okay, there we go. So I'm going to rotate this peroxy acid so that I have the O right there and the other O there, because remember that's really the important part of the functional group is that peroxy part. Carbonyl here, and then the R here. Let's draw our lone pairs on the O's. Are you ready? This is a doozy, so hold on. A lot of arrows for one step. But let's try to reason through it. Okay, so we know that heteroatom bonds are weak. So the order of drawing these arrows doesn't matter if you can make sense of it. So you can say, I am going to break this bond and let it go here so that it can open up the carbonyl. And when it does that, instead of landing on the O to make an O minus, it'll grab that H. And that'll save us a step, right? So we know it's not unhappy, it's not an O minus. That H has to let go of its electrons. It's going to give it to this O. But now that O has too many. So it's going to attack. But that alkene will not accept another set of electrons unless it attacks back. Okay? Let's look at the story of these arrows. Three-membered ring. That's what these arrows show. 2 bonds to oxygen. The alkene is gone. The electrons came up here for that. We keep the dashes and wedges the same. That's the beauty of using that perspective approach. Methyl and methyl. I'm not going to draw the H this time, just an effort to clean it up. What happened to the rest of it? I'm going to draw that because it helps us kind of understand what goes on, even though that's not what we're isolating. Our goal was to make an epoxide. But what happened to the RCO3H? Well, it lost this O, right? This O, I'm going to highlight it in yellow. This O is this O. Those are the same O. That O's gone. But look at the story, what the arrows are telling for the rest of it. This became an OH. This became a carbonyl. So let's draw it. I'm even going to try to draw it in the same orientation. So R, this became a carbonyl, right? That one over here became an OH. Hey, what do you know? We made an RCO2H. It lost an O, the yellow O. So what would you say happened to our oxidizing agent? It got reduced. It lost an O. Okay, so this is considered the byproduct, not a side product. There's a difference. A byproduct is usually something that forms alongside the main product, stoichiometrically, but it wasn't your goal to make it. So in other words, this was a fancy way, if it was our goal, to make a carboxylic acid. There are much easier ways, and this isn't the suggested way to do that. So in other words, that wasn't our target. This is our target. This forms along with it. Usually we have to purify and get rid of it. It's inevitable. A side product is a separate possible path. Like if you have, your goal was to have SN2, but you had a little bit of E2. That would be a side path, right? A side product, side reaction. So putting this in parentheses because I think oftentimes stoichiometrically, if we wanted to know what was going on, we'd have to write the byproduct. But oftentimes it's helpful to decipher what's going on in the mechanism. Now, I only showed you the top approach. Remember, there's the bottom approach. I'm not going to write the bottom approach. I recommend you do. What do you think it would look like? Well, it would have this on the bottom and all these same arrows only on the bottom, which result in this forming here on the bottom. So I will draw the answer for you. You could check. So you can draw, when you're first drawing it, you can draw your epoxide upside down, but you can keep the dashes and wedges the way they are here. That's the nice part about it. If you look at answer keys and the epoxide's not upside down, you do have to know how to rotate it and flip as needed. Okay? So here we go. The anti-methyls. So this was the bottom approach. Notice something that you can kind of take a step back and say, okay, I can start with an alkene. And notice it was trans, or in other words, E. Notice that that was maintained in our product. The methyls were anti here, if you will. They're still anti. That was preserved. Okay, so they're still trans to each other. All right. So the epoxide itself, by default, has to form on the same face. So the epoxide, we would say, is syn selective because both of those new bonds are on the same side because you cannot form a three-membered ring in an anti formation. That doesn't mean everything is syn to each other. That means that the ring bonds are syn. These were anti to begin with, so they're anti when we're done. Okay? So could you predict it if you had a cis alkene? I think so. Now we're going to do mechanisms many times. We already did the mechanism for this one. So now we're just going to do a simple predict the product. And look at what's drawn over the arrow. You might say, wow, what is that? I've never seen that before. You have to hone in on the functional part right here. That's RCO3H. So this is R. Oops. RCO3H. Don't let that scare you. This is a very common one, actually, where the structure is actually shown. So you have to know the abbreviation or the Lewis structure drawn out. This is MCPBA, which equals meta chloro peroxy benzoic acid. I'm kind of writing it with those, oh, well, that was the blank I had for it. MCPBA, okay? Let's draw our answer. And we have a Z or cis alkene. We're going to make both epoxides, top approach and bottom approach, and the methyls better be cis. Okay, sometimes they'll make it an enantiomer, sometimes it won't. In this case, it does not, because these are indeed the same. So you need to recognize that. So we have only one product. Okay. You try that one, and you can check your answer with me after we get back. Write out your answers. Draw the perspective, change it to dashes and wedges, and if there's more than one enantiomer, draw them both. Okay? I'm going to give you the answer right now, but pause or something. Okay, so this is MeCO2H, MeCO3H, excuse me. So we're going to do an epoxidation. And I'm going to do the top approach and bottom approach. That means I have a right side up and an upside down. Dashes and wedges maintain that same perspective I would have had. These are indeed unique. There you go. Did you match it? Racemic mixture.